Okay. Can I zoom out of this thing a moment? Let's see. Um, okay, here's where it gets a little strange. So the procedure actually changed for this lab a little bit, trying to make it online, or trying to make it easier the last semester, and then it suddenly became online, so it's kind of undergone this whole facelift. Um, let's not worry too much about the details of the procedure up here, and let's just kind of get the work done on this one. Um, so all these measurements here are in kilograms. All these masses are in kilograms, okay? Which is important to note. These are all in kilograms. The mass needs to be in kilograms for you to actually use it in F equals ma, the Newton's second law, okay? So it's a good thing it's in kilograms. We want to keep it in kilograms, and that's why there's such small values. Essentially, you can see here that the total mass in this box is going to be just the sum of the masses above. Okay, this is the mass of the first one's the mass of the actual cart. This thing does not go where I tell it to go. MC is the mass of the cart. MA is the mass added to the cart on top of the cart, and then MH is the mass of the hanger. So you can see what we did here is that the mass of the cart doesn't change, but the mass of the hanger, mass of the added weight to the cart switch places. And it's important because the mass of the hanger is the thing that's actually accelerating the system. That's the hanging mass down there at the bottom that's actually pulling the system off the edge. So you can see we double that, which means we'll double the applied force. The mass of the system stays the same though, right? It's 0.252 plus 0.04 plus 0.02 in parts A and B. So total mass shouldn't change there, but the force accelerating the system does change, right? Because mh is the only thing that's responsible for accelerating the actual system. And on this last part here, you can see that we roughly double the mass of the system. So on part C, we have 0.252 plus 0.312 plus 0.04. That's about double the mass. And so we should see about half the acceleration. Now, on this first box here, you're going to see this m total. You're just going to add up these three values and put it into this box here. So 0.252 plus 0.04 plus 0.02, put it right here in this box. Don't do any rounding, just leave it as a ugly little decimal for me. FH. FH is the force that's accelerating the system. That's the force due to the hanger alone, just the hanger. So to find FH, it's going to be mh times gravity. Okay? So, just another example of Newton's second law here. You would take the mass of the hanger, multiply it by 9.81, right? And that's how you're going to get FH. Okay, and it says it up here as well somewhere, but that's essentially what you're going to be doing there. So you want to do this box, you want to have it say whatever the mh is times 9.81, that's what that goes in the FH box, okay? Now, to find the next one, A measured and A theory. Okay. A measured is going to be from the experiment. A measured is going to be whatever's in the experiment, the actual data they gave you. So you're reading that from this plot here. Okay. A theory is going to be what you calculate. Okay. So to get a theory, you want to know the acceleration of the system. Well, the acceleration of the system is going to be FH equals the total mass times a theory. Yeah. Okay. So we have total mass. You find FH by doing, so you remember FH is equal to mhg. Okay. So mh times g. That's what FH is. And FH is also equal to total mass of the system times a theory. So put those things together and solve for a theory. And that's what you're going to be doing. Okay. So if you got any questions on here. So M total is the sum of MA and MH. It's the sum of MA, MH, and MC. It's the mass of the cart, that's what MC is, plus mass added to the cart. That's why it's called MA. It's mass added, I guess. And then MH is the hanger. So. Okay. So A measured is the next thing I talk about. So I'll write this down again on another piece of, or back on the notes as well. Let me just go ahead and. Okay, so here's A theory though before I move back to the notes. Part A plot, part B plot, and a part C plot. See? Okay. The plot is speed or velocity versus time, right? And then it gives you this V of t is 0.63 t right there at the top. Okay? That right there is going to be your equation of motion, or your equation of motion for this plot, right? That's going to be the equation of this plot you're looking at. That looks like y equals mx plus b, right? Where 0.63 is the slope. Okay, well, the thing we have to remember is that the slope of a velocity versus time curve is acceleration. Okay, so that's the thing we got to remember. So this is part A. You can see that the 0.63 must be my acceleration, right? And that's going to be my measured acceleration. Measured because it's essentially, if you were actually doing this lab, that's the one you'd be measuring from the experiment itself. Okay? So part A, it's 0.63. And that's what's going to go into this box up here. All right? And then part B, you can see it's 1.2. And part C, it's 0.59. Okay? So, M total is going to be MH plus MA plus MC. Okay? Just chat open. Okay. Let's see. What else? FH. That's going to be MH times G, with G equaling 9.81. Okay. That gives you FH. The acceleration theory is going to be FH over M total. Why is that? Because we have that equation of FH is equal to, or we have the equation of F is equal to MA, right? If I divide the M over, then I'll have just A. So the theoretical A, the A that I'm like hoping to find, is the one that I calculate, and that's going to be the FH divided by the total mass. Is why they give you, the first box is total mass, second box is FH. Divide those two to get the third box, or actually it's the fourth box. They skipped over, right? And as far as these plots go, these velocity versus time, you're going to have some slope. The slope is equal to A measured. Okay? So, kind of like going back to the equations of motion thing we did in the second lab, or whatever it was, third lab, we got to read the acceleration off of our graph. So we're going to have a part A, part B, and a part C for this. We have 3 different plots. So that'll get us our measured. Then you can do a little percent difference or a percent error, I think is what it depends on what it asks for. Okay. Also, I forgot to hit record on this until partway through. So, if you're here, you saw some of that early stuff. If not, then oh well. Okay. So let's see. Look at this lab again. Right. So let's see. So that's how you fill out the first chart, at least the first table. The next thing here is what happened to the force FH going from part A to part B. We already calculate FH, right? Yeah, FH is just MH times G. All right, so you have MH right there for part A, it's 0.02. So you do 0.02 times 9.81, and that's going to be FH box. Okay? Same thing over here. Part B, 0.04 times 9.81, that'll give us the FH box. The next part down here, what happens to the force FH going from part A to part B? Just a simple question, right? You're going to fill out this box up here. And what you should notice is that FH for part A is going to be about half as big as FH for part B. Really, because it's just 0.02 times 9.81 or 0.04 times 9.81. So you can see one's larger than the other by a factor of 2. So what happened to the force FH going from part A to part B? It got doubled, right? That's all they want to hear. That's all that's asking. So don't overcomplicate any of that stuff. What happened to the total mass going from part A to part B? Well, you can see it's 0.252 plus 0.04 plus 0.2, 0.252 plus 0.02 plus 0.4. It's the same, right? So nothing happened. They're the same. Okay, what happened to acceleration going from part A to point B? So it's just, you're just answering some very qualitative questions. Really nothing too deep, at least in this first part. Okay, so it almost seems like you wouldn't even really need to say anything here. It's kind of obvious stuff, but just go ahead and just write it out for me. For the A measure, could you integrate the given velocity, then plug in time to get the A? Integrate as in, so this V of t is equal to 0.63 t thing. So if you integrated that, you would actually get a position function. So what you would want to do is you want to find the derivative. Yeah. But then once you find the derivative, you'll see that t goes away, right? And you're just left with 0.63. Yeah. So it's literally like we're just going to read it. It's like we're just reading it right off the graph. But yeah, that's a good observation, because what you're really doing is you're finding the derivative, right? You take the derivative of that thing. The t has a power of 1. The 1 comes down. The t's new power is 0. So the 1 multiplies the 0.63. It's still 0.63. The t has power 0, so it's 1. So it's just 0.63. And what we've really done is we actually did take the derivative, and we actually did find an expression for a of t, the acceleration as a function of time. But time went away, and it really just reduces to we're just reading the slope off this. We're just reading this number here. So yeah, A measured for part A is this 0.63. A measured for part B, 1.2, so on and so forth. And then they just ask some more of these qualitative questions here. Just, hey, what happened to the force? What happened to the mass? What happened to acceleration? Okay. I'm going to let you guys fill out this chart really quick. That's pretty much all you have to do for the first part, and then I'm going to start talking about the questions, okay? Like I said, I'm just trying to I don't want to have everybody agonize over this lab too much. I kind of just wanted to help you through it, just talk about it. The only useful concept here is this F equals ma stuff, which we'll use again later. It's actually, the questions here at the end are more useful, I'd say, than the rest of the lab really is at this point. And okay, as far as the percent error, it doesn't want percent error. Is it? Yeah. So as far as percent error goes, you're going to do A. Is it between the A's, right? Yeah. A measured minus A theory over A theory times 100. Okay? That's the one we're going to use. All right, and I'll be right back. Okay, good. I see people working together. That's what I want to see. Is everybody good? Again, sorry for being late this morning. My computer had a hard time starting up, and by computer I mean my brain. You know. So let's see. As far as this filling out the chart thing here, okay, for the percent error, do we? No, it's not that one. It's Emily. Go ahead and look at the screen share. It's this one here. So whatever your measure is minus theory divided by theory times 100, and it's okay if it's negative. As far as percent errors come, they can be negative. That just tells us that the value that we got was below the value we expected. Weird numbers, huh? How so? Let's see. I'll work along with you guys on this. How about that? Part A. M total should be, let's see. Error increases a lot from part A to C, yeah. Yeah, I bet it does. It's okay. I mean, as long as you're doing the calculations correctly, you might get some weird. I'll go ahead and verify now with you guys. But weird error, like bigger errors are okay. It's fine. I'd actually rather I grade a little easier if I see someone with like a freaking 15-20% error or something crazy than I do if I see someone with a 0% error. If I see 0% error, I'm usually like, okay, you rounded and you made it perfect, but so yeah, big errors are fine. Don't be concerned with big errors. You see big errors, that's fine. So FH in this one would be 0.02 times 9.81, which would be A measured for part A would be 0.63. Yeah, I'm writing units down, but I mean, I kind of feel like I don't want to do that. Okay. A theory would be okay. Here's a perfect example, everybody. I want you to see this. Look at my notes here. Okay, I got 0.628846. So okay. I do not want to round that to 0.63. If I round this to 0.63, I'm going to get a 0% difference, and it's going to be boring. Okay. So at most, round it to 0.628. Just because I see that 0.6, if I rounded it to the hundredths place, that it's going to be identical, and I don't want that. That's the only reason I'm not going to round it to hundredths place. Okay. So 0.62885. I'm just going to leave it at 0.62885. Okay. So then my percent error is going to be 0.63 minus 0.62885 over 0.6. So here I got 0.1828, so I'll round this to 0.18%. Okay? Anyone else get that? 0.18%? Yeah, I'm not trying to harp on you if you did round to 0.63. Guaranteed someone rounded to 0.63. Don't do it. Alright? Just please keep it like that. Well, that's okay. I mean, okay, any of those is fine. Any of those is fine. That's okay. It just means that, like, you might have rounded to a slightly different decimal place or something. That's fine. I'll look at the work you did and it'll make sense. I just don't want to see a zero. That's all. I'm just trying to avoid 0% differences. That's all. Okay. 0.32. I mean, I guess I don't know. It's almost exactly double. I don't know. Yeah, if I round this a little bit, it would be a little different. That's fine. Okay. There's part A, right? And that's essentially I want for part A, B, and C. If I should write this out. This should be the same. FH would be the mass of the hanger, 0.04 times 9.81 to give us 3924. Okay. What's A measured for part B? Part B simulation down here. I got 1.2, right? 1.2 meters per second squared right there, reading off the chart. I'll just complete this one. I'll leave part C for you, I guess. I don't know. And then A theory is going to be FH over M total. So it's 0.3924 over 0.312. And so that gives me, hey, 1.257. All right, and then I do 1.2 minus 1.257 over 1.257. Okay. Yeah. So much bigger percent difference, percent error in part B than part A. That's fine. And it's negative. Okay. So part C is just like that, but just for different numbers. Cool. So that's all you need to do for the first part. Then you're gonna answer these very ridiculous, like, busy work questions. Not even busy work. It's just a quick answer. What happened to the force FH going from part A to part B? Okay. So if I look at my shared screen here, from part A, my FH is 0.192. For part B, it's 0.324. That looks like it's about double. 3924. 3924 divided by 2 is 0.1962. So look at that, it's double. So we found that the part B's FH is double part A's FH. Okay? Because we doubled the mass of the hanger. Makes sense. Number 2, what happened to the total mass? Stayed the same, right? Total mass 0.312. Over here, total mass 0.312. What happened to the acceleration from part A to point B? Okay, so what's the acceleration over here is 0.62. Over here it's 1.2. That looks like 6 and 12, kind of, right? It looks like it doubled. So if I do 1.257 and divide by 2, I get 0.6285, which looks pretty damn close to what I had over here. So it looks like my acceleration doubled, right? And then same kind of questions over here and over here. Cool? Okay, so I think I'll start talking about the questions now. Well, you know what? I'm actually gonna watch this video later. You can see me posting a quiz. This will get enumerated. Alright. Yeah, I did a little... Okay, safe to say accelerations in part A and C are about the same. You know what? Turns out, I don't know. Yeah, due tonight by midnight. If you're gonna have... If that's gonna be a problem and you're gonna have some trouble, let me know. But... Pro tip, keep my practice exam open while looking at the normal exam, okay? Or the not exam, quiz. I just want you guys to solve some problems, that's all, okay? Just want you to think about it, and I'm not trying to see how fast you can get an at-home exam or quiz done. Not trying to see if you can get it done in an hour. I'm trying to see if you can do it. And that's why it's all day. Part C. I have not, to answer your question there, I have not looked at the accelerations for part C. But what is acceleration for part C? Good question. Let's find out. And the total mass is different. Right, it's 0.252 plus 0.312 plus 0.04. So 0.604. And FH is same as the last one, yeah, 0.3924. So acceleration theory should be hey, yep, looks like it. Thing is, we doubled the amount of force accelerating the system, but we also doubled the mass, right? So how much percent error can accept? Well, it should be like, within a few percent error. It should be like, two digits. It shouldn't. You shouldn't have any like 100 or something percent, but it should just be like, what number are you getting here? Part C simulation is 0.59. Okay, so 0.59. So 0.59 minus 0.6496 over 0.6496 times 100. What do I get? We've got 9.17% difference, a negative. Right? And there you go. So that's fine. I don't know what percent error you had, Sultan, but 9's fine. This one was 4, and the other one was less than 1. Alright, so I pretty much have all those chart stuff on here. I'll submit this later on so you guys can look at it on Blackboard, but I pretty much have the answers. Look at that. Ooh-wee. Ooh-wee. Let me go ahead and post this quiz. Quizzes are only 5 points. Labs are 15. So you're going to be able to submit it in the assignment section. There's lab 5 for Newton's second law, thing we're doing today. There's also a quiz 1 link. So you can submit it there. And in the quizzes section, it's posted. All right, I know it's also kind of low tech because I hand wrote it. But generally pretty neat handwriting. If there's any problems, let me know. Okay, questions. Number 1, let M1 be some mass and F1 be some force acting on that mass. The numerical values are not important. Write A1 in terms of the other two variables given. So guess what? This one should be pretty straightforward, right? We have M1 and F1, and we want A1. Well, do we know of an equation that relates F, M, and A? We do, right? Newton's second law. So we should say F1 is equal to M1, A1. If we want to write A1 in terms of the other two, that means we need to solve this for A1. So we have F1 over M1 is equal to A1. Cool? Suppose that we double the mass of the object in question 1 so that M2 is equal to 2M1. We maintain the same force, so that F2 is equal to F1. Express A2 in terms of A1. Okay, so this is the thing that I usually... This lab, I usually at this point go through all this stuff with everybody anyway, so I'm kind of doing it with you now. So we have some system that's F2 equals M2 A2, and we have F1 equals M1 A1. Okay, so we want to find A2 in terms of the other ones. So we have A2 is equal to F2 over M2, right? Okay, so we're just solving that Newton's second law right there. But what they have told us is that F2 is equal to F1, and they've also told us that M2 is equal to 2M1. Okay? So go ahead and make those substitutions. We have A2 is equal to F1 over 2M1. Okay? You know what that looks like? It looks like 1/2 of F1 over M1. Okay? And F1 over M1 That's this. Right? So that's actually just 1/2 A1. And we've done it. We've written that A2 is 1/2 of A1. Okay? This is a... I wish I could make a bigger deal about it or make it easier to show you guys other examples of this, but this is kind of an important thing in physics. You'll always see some question that's like, what if we double this? What if we half that? Or whatnot and so forth. They'll ask what if we double or half or something? What happens to some other value, right? And the thing is you always want to actually you don't want to do that mathematically. You want to do it symbolically. You want to do it analytically like this. You want to replace this thing, let's say this M2 with two M1s like we did. And then notice that I looked for the old expression, this F1 over M1. I looked for that in here, in my new expression. I was looking for that in my new expression because as soon as I find that, I can isolate it and then replace it with A1. Right, so the answer here is if I double the mass, I half the acceleration. I get 1/2 of the old acceleration is the new acceleration. Usually I make a bigger deal about this, but again, it's online, so it's kind of like hard to. Let's see. Bonus example, I guess, would be. So I have some system. The accelerator system A. Okay, so I have a system. So let's see. Okay. Another example here. I have a system, just some M1, F1, and A1. What happens to A if I double the mass and quadruple the force? Okay. So my old system is F1 equals M1, A1. My new system is going to be like some new force, some new mass, some new acceleration, right? So I can go ahead and say my new acceleration is going to be some new force over some new mass. But I've already said that I double the mass and I quadruple the force. So that means that A2 is actually going to equal 4F1, quadruple the force, over 2M1, double the mass, right? I can bring out that 4 over 2, which is just 2, obviously, but you can bring that out, and then I can have this F1 over M1 isolated here, because I'll know that A1 was F1 over M1, right? That would be like what my old acceleration was, just if I solved F equals ma formula. And therefore, this F1 over M1 I can substitute out with A1. So A2 is equal to 4 divided by 2 is 2 A1, right? This is a separate example. This is not question 2. This is a bonus. But I'm just kind of like showing you guys again, if whoever's paying attention, this concept of keeping it in, symbolically and then doubling the terms and then isolating your old expression and then replacing it with what you had that old expression equal to is a very common thing in physics, and you'll do it a lot. Okay. Usually I make more of a bigger stink about this, but this doesn't feel like the most organized way to do it right now. Okay. Cool. So talked about a couple of the questions. I don't give everything away. Suppose instead we double both the mass and the force. Okay. So I did a bonus, and I did the first one. So now you guys go ahead and... I did the second one, and then I did a bonus. So you guys go ahead and tell me the third one. So it's just like number 2, except we're doubling the mass and the force. Write it like I have on this paper over here, and tell me what would happen. What would my A2 would equal what times A1? 4 gravitational force acts on all objects in the cart and hanger system, including the cart's mass MC. Should we have included F equals mcg in our calculations? Equations. Okay, everyone. Number 4 is written kind of confusing, I think. It's written a little strange. So let me just say... Jesus. So this cart was up here, right? And then we had pulley, and then we have hanger mass down here, right? The hanger mass is the only thing that accelerates the system. Okay? It's the only thing. It's because gravity's pulling on it, it's hanging, it's being pulled like along the direction this thing wants to travel, down, right? Which is then pulling this thing up here to the right. Okay? There's no friction, so we don't really care about what's happening up here. We don't care. Okay? So number 4 says something about should we have included F equals mcg into our equations. So mc is actually the mass of the cart, right? There's a little block on top, and that's mass A, okay? mc's mass of the cart, mh is down there, right? We could have made... I don't have to squish this thing so damn close to the roof, do I? Okay. Anyway. So, the short answer is no. We shouldn't have included anything like mcg. Because the thing is, this fh, which is equal to mh times g, that's the only thing accelerating the system. Mcg would be this force here. Ignoring this should be ma. Ignoring the little MA on top, this right here would be FC would be like, MC times G. Okay? That has no effect on the acceleration of the system. There's one reason for that. The main reason is it's not pointing in a direction that the system would accelerate, right? It would have to either point this way, up there if you're up at FC, or down if you're over here at MH. That would accelerate the system, right? See, this thing here is just pulling it against the table, okay? That does cause friction, right? That's what's called the normal force, and that would be, we would use mcg to find the friction that cart experiences with the table, right? But in this situation, we're ignoring friction. There's zero friction. No friction. So we ignore FC. Okay? So that's me answering number 4, because number 4 I think is just written a little strange. So do number 3 on your own. I did 1 and 2 for you. Alright, so that's pretty much the whole shebang there. Here's an example of how to do one of these problems. Alright. So go ahead and post it in the chat if you need something. I'll be right back again. this? Like, where's my cat?
Oh, you didn't recognize the meme? Oh, okay.
No.
It's the guy from Pulp Fiction. John.
Oh, yeah. How far is your car? Alright. Love you. Alright. How's everybody doing? Problem 4. Okay, so mcg would be the force. Well, actually, so that mcg would be the weight of the cart. Okay, so that's another way to think about it. F equals mcg equals weight of cart. Now, the actual force that the cart is applying to the table it's on would be what this weight of cart thing is. Like we do care about the mass of the cart because that affects the acceleration of the system. Okay, we do care about the mass of the cart. We do not care about the weight of the cart. Okay, so I care about cart mass for lab, but don't care I don't care about the weight. Now, the reason why I don't care about the weight is because the weight is this FC right here. Okay. I don't care about that because it's not really pointing in the direction that would accelerate or decelerate the system. Right? It's just pointing against the table. So it's presenting like a normal force between the cart and the table, just sitting on the table. Now the thing is, normally we would use that normal force to calculate the friction, and the friction does point along the direction of travel. Okay. The normal force does not. But here I'm assuming there's no friction. So, in essence, because of the no friction surface, I don't care about mcg. Okay, so that's essentially it. Yeah. It doesn't point. MCG does not point in the correct direction, the direction that would actually change the motion of the system. The only way that FC could have any effect on the motion of the system is because of friction, and there's no friction. So, in short, we do not care about FC or MCG. We don't care about. I called it FC. Does that make sense? Hopefully. Jesus. Okay. I'm sure so many people got excited. Maybe no lab today, and you're thinking, oh man, I didn't have to get up. Man. Oh. Looks like I missed something from Marissa, too. The reason we do not include...
Чего ты какие-то что?